Good afternoon, ladies and gentlemen. It is a pleasure for me to present this lecture about better bonding through the water jet technology. I'm Johan Silfwerbrand. I'm a professor in structural engineering and bridges at KTH, the Royal Institute of Technology in Stockholm in Sweden. So I have received some questions that I will end the lecture by answering. Perhaps you can answer them already now, but with some help from what I'm going to say. So what is bonding? What is selectivity? What is important to, why is it important to clean the surface or the substrate before recast? And why are jackhammers damaging the structure? And so the outline will be, I will try to explain why it is important to remove poor and damaged concrete, and how important it is to achieve good bond. And then the main part of the lecture will be devoted to factors influencing bond, and then among these is we are taking advantage of the selectivity of the water jet technology. So in first slide here about removing poor concrete. Deteriorated concrete has low strength and leads to reduced load carrying capacity. We are quite often using the water jet technique on for instance, bridges where we have a lot of damage due to the use of de-icing salt, the use of weather, the use of the frost, and with the use of a lot of vehicles that could lead to some kind of fatigue. And as the de-icing salt is perhaps the main purpose and the main damaging factor, it contains the concrete that you have. It contains detrimental substances, that is chlorides from the de-icing salt, and they may damage also the new concrete, or especially if we have reinforcement in the new concrete, and that we often have. The concrete and the reinforcement doesn't like chlorides, then it starts to corrode. And then also the deteriorated concrete, it is quite often full of cracks. It is porous and it is water permeable. So we need to remove it in order to maintain the original concrete that is still sound, that it could maintain to be sound. And then if we have a damage on a concrete, we normally also have reinforcement corrosion, and then we need to uncover the reinforcement and clean it from rust. And if we have lost a lot of area, we need to place some additional bars in order to restore the load carrying capacity. And when we are removing poor concrete, it is also important that we are going behind the reinforcement, because we need the old reinforcement that we are keeping. It needs to have a decent surrounding of new concrete to provide a good bond between the reinforcing bar and the surrounding concrete, and that we have tested. So in a series of tests, we were making slabs, and then we were removing concrete from these slabs, and then we used the new concrete. In this case, we were using shotcrete, but we could also have used cast concrete. It is not that important, the difference. The thing that we were concentrating on was the location of the rebar in compared to the interface between new and old concrete. So we looked at three alternatives. We had a very thin overlay, so then the interface is in the substrate A. Then we have a case where we have coinciding interface and rebar plane. So we have the interface between substrate and overlay inside the reinforcing plane. And then we made a very thick overlay. So we went behind the rebars completely, and then we cast the new concrete. And here you can see from the slabs we cut beams, And then you can see the 4 types, A, B, C, and R. R is a reference case that was just in the old concrete. But you have the composite beams in A, B, and C, but the difference is where the interface is located. And then we tested both static load and fatigue load. So fatigue load, that is some kind of dynamic load of a lot of load repetitions. And you can see that the beams were simply supported, and we had reinforcement in the bottom. And then you can see that it was quite interesting that we received various types of failures. So on the A, where we had a very thin overlay, observe that the overlay is in the bottom. So we made the slabs, the beams opposite time, upside down, which is more interesting for the purpose here. So we received a ductile flexure failure on A, and the same on C, where we have the thick overlay, which is going behind the rebars. And then also for the reference, we also received the ductile flexure failure. But on the B type, we received the brittle shear and anchorage failure. As you can see, the horizontal crack on the left-hand side of the B beams. And that we always want to avoid the brittle failure, because that is sudden and it is more dangerous than the ductile failure. And remember, in the B beam, we had a coinciding reinforcement and interface plane. And then also very interesting in this test series was that when we made the fatigue test, you can see that we received flexure failure for A, C, and R beams, but we received shear failure for the B beams. And you can also see that the number of load repetitions to failure, that was 20,000 for B beams and 200 to 300,000 for A, C, and R beams. So also here we can see that it is a very obvious result. So if you see the when you are water jetting, please if you will see the rebars, you have to continue the water jet removal behind the rebars. So the importance of obtaining good bond, I think there are several reasons. Here are 4 of the most important ones. It is mandatory for producing a repair structure that carries load monolithically. So the old and new concrete, they work together as a monolith. And then if it is able to carry the load in a monolithic way, then it increases the strength or the load carrying capacity of the repair structure, and it also increases the stiffness. And if you increase the stiffness, you will receive smaller deflections. And then also good bond that promotes crack control, and it prevents water transport along the interface. So this slide shows the first thing I said about the load carrying capacity. If you have a good bond, you will have smaller stresses because you have composite reaction. And then if you do not have any bond, then the 2 parts of the beam will act separately, and you will have twice as large stresses, and that could lead to cracking. And here is to show you the difference in if you look at the stiffness. It is even more obvious than if you look at load carrying capacity. If you just have one single beam, then and for this simple case, you have a 500 millimeter deflection. If you place 2 beams of similar height on top of each other, you will reduce the deflection with 50%. Because they are taking half of the load each. But if you glue them together, if you receive bond, then the thickness will be twice as high, and the stiffness will be 8 times higher, 2 raised to the power of 3. So you will just have 60 millimeters of deflection instead of 500 millimeters. So that is very important. This slide is from a colleague of mine, Jonas Silfwerbrand in Luleå, in the very north of Sweden. He made his PhD and he was also looking at overlays, and he looked at a case where he had a good bond between the base and the overlay, and you can see here that after some days and weeks, he received some minor cracking due to the differential shrinkage, because the new concrete will shrink and the base is preventing that shrinkage to be free. If you have bond, and you will have a lot of small cracks, but all of these are harmless. So it is not a problem with these very small cracks. You can see they are 0.1 and 0.05 millimeters, so they are harmless. But he also tested some of the beams. He deliberately broke the bond, and you can see here the gray area. There is areas without bond between the two layers, and here you can see fairly large cracks, 1 millimeter, 0.7 millimeters, etc. already after the 6 days and so on. And these cracks will continue to grow together with when the shrinkage is developing further. But normally you have just 1 or maybe 2 cracks, and then all deformation is concentrated here. So this and this, of course, if you have cracks that are 1 millimeter or more, then that will be detrimental for your durability of your reinforced concrete. And here is a final slide about importance to receiving good bond. And you can see here that if we have poor concrete in the interface zone, then if there is a horizontal vertical crack, then water will penetrate to this interface, and then it will have a transport road to pores in the poor concrete. And then when the water is freezing during winter time, we can have frost damages. So this is a fourth reason to receive good bond and remove all bad concrete. Okay, so now this is a slide showing the factors that may influence the bond between old and new concrete, and these are in chronological order. So you have everything from the substrate properties to the environment of the repaired concrete structure. And here is another way to show you these are the main factors, and there's a lot of research behind, and we were able to identify the 5 most important factors influencing bond, and that is absence of microcracks, it is absence of the latence layer, which is a soft layer in top of concrete. When you cast concrete, it could be some kind of segregation, and then will be rather a weak material at the top. And that you should remove. And then it is important that the concrete is clean when you are casting the new concrete overlay on top. Otherwise, you will destroy your bond. And then you should compact your overlay carefully in order to get rid of all air pores, the large ones. The very small ones are beneficial for frost resistance, but the large ones, they need to be compacted, and then you have a homogeneous overlay. And then it is important to cure your overlay properly. So these are the main factors. There are some secondary factors, that is pre-wetting, that is you have some moisture on top of your substrate at the time of casting the overlay. It is about the overlay properties, like the strength of the overlay, and it is time after casting. All strength properties of concrete need some time to develop, and it is the very same with bond. And then there could be some other factors like substrate properties, the roughness, bonding agents, how you place your concrete, early traffic, fatigue, environment factors, but these are of the 3rd level. So I will speak some words about the 5 main factors first. So we have this absence of microcracking, and microcracks reduce bond strength substantially. That has been shown in several research projects. And the reason is their detrimental effect on the uppermost layer of the substrate. The microcracks, they are rather superficial, but still they are producing a top layer of the original concrete that is weaker than the base. And by selecting the method of concrete removal carefully, microcracks can be prevented. And you can guess that water-jet technology is among these methods. So here you can see these are some methods that are used for repair and improving the surface. And on top you have sandblasting and shot blasting. And of course, they are quite good in cleaning the surface, and they are not causing microcracking, but they do not have any depth action. So if you need to remove some centimeters of concrete, they are not a realistic alternative. Then you have grinding, and that could go some deeper. We do not know exactly the amount of microcracking after grinding, but I guess that there could be some, and still it is not a method that has a large depth action. And then you have milling, and then you have jackhammers, and of course you can remove a lot of concrete with these two methods, but unfortunately they are introducing microcracking. And then finally we have the water jetting, or the water jet technique, and it has a depth action. You can remove several centimeters, and you can continue if you wish to remove more concrete, and the amount of microcracking is very, very small. And so the water jet technology, it works with you have the water jet and these thin water jet. It builds up a water pressure inside your concrete, and when the water pressure exceeds the tensile strength of concrete, the concrete spalls. And if your concrete contains a lot of cracks, it contains a lot of pores, other types of distresses, and if it is of poor quality, the water jet technology, it works much more efficiently, and that's why it is also selective, that it removes poor concrete and it leaves good concrete. And you know much more about water jet technology than I do. I know its effect. But we have in Sweden, we have studied water jet technology for bridge repairs since the mid-1980s. And here is the first equipment that was used in Stockholm. I think it was in 1984 and 85, with a very good result, in fact. And this is another equipment from a little later stage. And one question here was about selectivity. And in fact, we have tested selectivity in the lab. And then we cast some slabs, and we made them of two types of concrete. And then we looked at the result. And the ambition was to remove all low-quality concrete and keep all good quality concrete. And so here you can see that there were two stairs. The red color here, that it shows the high strength, or it is a medium strength concrete, 40 megapascal in compressive strength, and the blue is 20 megapascal, which is a low strength concrete. And you can see one stair is going from the left to the right, and the other one from the right to the left. And we tried various equipments, or the companies. They wanted us to test their equipment to see if the technology was able to work selectively. And here you can see another sketch of a beneficial result that you have. Here is other colors. So blue is still 20 megapascal, but the high quality is here 40 megapascal. And you can see that we have. This is a result where you have left most of the 40 megapascal concrete, and you have removed most of the 20 megapascal concrete. So good result. And in order to make it a little bit more complicated for the equipment, we had also reinforcement meshes, both in the top and the bottom of the specimen. And here is another how we look at this after the water jet technology, and you can see that we have removed most of the blue concrete. And in fact, the Swedish, at that time, it was the Swedish National Road Administration which developed some recommendations for approval of equipment. And you can see here that in order to use the equipment selectively, the result must be inside the green area in the bottom right of this diagram. And you can see that one example of fulfilling the requirements, that is to remove more than 90% of 20 megapascal concrete without removing more than 25% of the 40 megapascal concrete. So it was quite difficult I think quite strict requirements. And here is a summary of tests from 5 different companies with 5 different equipments. And I call them just A, B, C, D, and E. And you can see that we didn't just look at selectivity. We looked also at other types of results. But here I'm concentrating on selectivity. And you can see that the equipment A, C, and D, they were able to work selectively. The others can just be if you are selecting one of the other 2, you can just use the water jet equipment for removing a certain depth. But it is much more. We want the selectivity, and it is absolutely possible to receive it. Now, one very good, as I mentioned already, that the procedure of removing concrete by using water jet technology, it doesn't introduce any microcracking. It is perhaps a little bit exaggerated. There will be some microcracking, but they are of minor importance. If you compare it with jackhammers, pneumatic hammers, that it is a very large difference. And here is from a thin section analysis. And you can see to the left, you have these cracks marked with arrows on a jackhammered surface. And on the right-hand side, you can see a water-jetted surface without any cracks at all. This has a rather important influence on the bond. So if you compare, and this I did in my PhD thesis, it is a long time ago, but the results are still valid. You can see, and here was a comparison between water jet and jackhammers. And you can see that we have microcracks in the jackhammer, and we obtain a failure stress, a bond strength of about 1 megapascal for that case. And if we use the water jet technology, we received twice as high bond strength. Sometimes 1 megapascal can be sufficient, but in lot of circumstances we want to be closer to 2 and observe this was in the lab. In reality, we rarely reach the same values. So then it is very good to have a lab value which is about 2 megapascal, but because then we can be certain that we will receive at least 1 megapascal in reality. And I'm not the only one who has tested this. So the Bissonnette is a researcher from Canada, and he has also made a lot of research in the area of concrete repair, bonded concrete overlays, and you can see that his results are rather similar. They are from a later date, but you see that water jet about 2 megapascal, jackhammers 1.3. Very clear difference. And another international researcher is Luc Corrar from Belgium, and he developed a method to measure the microcracks. And here you can see the comparison between jackhammers with the weight of 7, 14, and 21 kilogram. And then you have the high pressure water jet. And you can see that there are some minor, the small length of cracks also for the water jet technology, but they are much smaller. And another observation you can do is that the heavier jackhammer you have, you more microcracks do you have. So if you in some circumstances, if it is impossible to use the water jet technology, I would advise you to start with a heavy jackhammer and continue with this with a minor one, because then you will make a somewhat better solution. Okay, so that was the first very important factor. Perhaps the number one, which is the absence of microcracks. And then the next one is absence of the latence layer. And I think I have already spoken about this. It reduces bond strength markedly because the material itself has a rather poor strength. But if we are in the repair business, we are always removing old concrete from the surface, and then we are at the very same time we are removing the latence layer. So in reality, this is not a real problem. It is a problem for in the when you are making buildings and you are using precast hollow core slabs for buildings, for office buildings, for instance, or for apartment buildings, and then quite often you are putting a overlay on top of the hollow core slab to make an even surface. And then if you want to have bond in these cases, you need to at least sandblast or shot blast the precast slabs before casting the overlay. So this is, I have already said it, I can skip that. The next one is about cleanliness, and the substrate surface has to be free from dust, oil, pollutions, and loose particles, because they will destroy your bond. The water jetted surface has to be clean immediately after water jetting to prevent cement paste from adhering to the surface. When you are using water jet technology, then you are removing a lot of concrete. And it is not always the case that all cement paste, all the cement has hydrated in the old concrete. And now you could there is a risk that you are exposing unhydrated cement surfaces for water. And then if you have loose particles, they may adhere to these free cement surfaces, and that's why it is so important that we remove the debris after water jetting, and do it quickly. It is a combination of with the water that you have, or the moisture. And then if it takes some weeks before between the water jet operation and the casting of the overlay, you need to make a second cleaning. It might be necessary immediately prior to the overlay placement to remove dust from construction traffic, or if you have a polluted environment. And the cleaning methods are use clean water with a high pressure, but not that you should not use water jet technology anymore. So it is a medium high pressure, of course, at an large flow. And exposed rebars must be cleaned from rust. They are cleaned when you are using the water jet technology, but then if it goes a long time before water jetting and overlay casting, then you perhaps need to clean them a second time. Another important thing, when you when you add your new concrete to you cast your new concrete, then the compaction of the overlay is important, and to obtain a dense and homogeneous overlay, as well as a good and even bond. And also when you have a water jetted surface, it has a lot of valleys, and in order to get rid of the air pockets in these valleys, the compaction is very important. And the Swedish Transport Administration, it recommends vibration pokers and vibration platforms to use, also traditional tools. But experience also shows that you can use self-compacting or self-consolidating concrete if you wish as an alternative, and that works also very well on the surface. And here is just a photo showing the vibration poker and vibration screed. Curing is also important, and because early age shrinkage, they may cause some overlay cracking. And if you have some overlay cracking, there is a risk that you will have a concentration of shear stresses in the vicinity of the crack and also at the edges. And these shear stresses might exceed the bond strength, and then you could have a crack that develops a horizontal crack in the bond that which is called debonding. And this debonding process, it starts at the edges and starts at the cracks and develop to the interior parts. I don't think this problem is that big, but in order to reduce the risk of this, you should cure your concrete properly. And here is some calculation example that if you have poor water curing, you will have stresses that are 6.6 times the strength of tensile strength of your concrete. And if you have 7 days of water curing, you could reduce it to 0.5. So it is a clear difference, and that shows. And the reason is that if you cure your concrete properly, you are also promoting the development of tensile strength, and then you will have more tensile strength when the concrete starts to shrink, and it doesn't start to shrink before you have closed your curing. So this is a theoretical slide, but it shows the importance. And there are also other benefits of a good and prolonged curing. You will reduce the debonding risk, as I have said, and also the risk of shrinkage cracking, also the risk of plastic cracking, which appear very early. You will have increased strength of your overlay. You will have increased durability of your overlay. And if you are going to drive your car on top of your bridge deck, which is composed of this overlay, then you will also increase the wear resistance of that material. So why not? If you are spending a lot of money to repair a bridge, why couldn't you cure it for a week? And here is another slide. Start the curing early, and then you may start by using some membrane curing, and then you can come back with some mats, which you keep them moisturous during the entire curing time. I have mentioned the 5 most important things, and then some more. And the one of the secondary factors is pre-wetting of the substrate moisture, and this is some reasoning. A too dry surface may absorb water from the fresh concrete overlay, giving risk of a heterogeneous porous zone close to the interface. And if you have a porous zone, you have a lower strength. A too wet surface, on the other hand, that causes an overlay zone with a high water-cement ratio, and a high water-cement ratio that leads to a low strength. And then there is a risk that you will have a poor interface, and that is not promoting a good bond. And then free water at the surface that may destroy the bond completely. It is very difficult if you have, and I have investigated a damage on such a site, where they cast concrete the day after a heavy rainfall, and that was very poor bond because they had a lot of free water, and they are not using concrete for underwater repair, which you never do on land. And this is just a principal sketch that the difference between very dry and pre-wetted and wet, that there are rather small differences, but if you have free water, you have a poor bond. Another thing is about the overlay concrete mix. Consider compatibility between the substrate and the overlay. Selection of similar materials reduces the problems. Similar repairs with similar materials, or like with like. Likewise, that is a rule of the thumb. Difference in strength and stiffness is not decisive, however. The problem is exaggerated, but still I think it is good to use concretes of similar types. Select largest possible particle size. in your aggregate for the aggregates, considering overlay thickness and reinforcement spacing. But it is as large as possible, because if you have larger particles of your aggregate, it will shrink less. And shrinkage limitations reduce differential shrinkage, crack risk, and crack width if there are any cracks. And then overlay strength. Shear failures often occur inside the overlay, close to the interface, according to Boyshausen, which is a South African researcher in this area. And this proves the existence of an interfacial transition zone. So that means that you shouldn't use too poor concrete for your overlay. You should have at least moderate quality. I wouldn't go less than 40 megapascal in concrete strength. And then this is the overlay strength, and here is from the reality. And quite often the old concrete, you cannot remove all old concrete, because then you do not have any bridge to make your overlay on top of. So you need to save some part of the old concrete, and sometimes the quality of that material is not of the top quality, and then you will have when you are testing the bond, you will have a failure inside the old concrete. And so that means that independent of the quality of the new material, you can never surpass the quality of the material that you leave behind. And this slide is from some tests that you can see that the development of bond strength, if you have a water-jetted surface, it is very, very fast. So it is a lot of scatter, I admit, but you can see that already after 24 hours, 1 day, we exceeded 1 megapascal in bond strength. And this is beneficial, because then we know that you can use your repaired structure quite early after casting the concrete, because the development of bond strength is so rapid. It is much more rapid than the development of compressive strength. Roughness, that is a less important factor. That I have read so many reports of rockies in the area of concrete repair, and they all think that, the roughness, that is the number one factor that is influencing the bond. But unfortunately, they all will come to the same conclusion, that it has a minor importance. And I can show you why from my old tests. And this is just to show you water jetting versus pneumatic hammers. The roughness is twice as large for water jetting as pneumatic hammers, but that is not the reason why the water jetted surface is superior. So here is a comparison with two more extreme surfaces. I'm comparing the water jetted surfaces with the sandblasted surface, and here we do not have any micro cracks in any of these two cases. And you can see that the failure stress is almost the same. It is 2 megapascal for both. And you may think that sandblasting is better, but that is a reason for just due to scatter. We have always bond failure is a tensile failure, and we do have always a lot of scatter. So water jetting is as good as sandblasting, but you cannot use sandblasting to remove concrete, because you just take 1 millimeter by using sandblasting. But here you can see that the roughness has a very small influence. The water jetted surface is 8 times, it is 16 times larger than the roughness of the sandblasted surface. So on the surface roughness, the importance of surface roughness is greatly exaggerated. In practice, hardly any difference between water jetting and sandblasting. Possible FFX. Johan Silfwerbrand, jag föreläser. Excuse me, I know how to close my cell phone, but not my ordinary telephone. In practice, hardly any difference between water jetting and sandblasting, and there might be a threshold value and if there is one, the roughness is even smaller than that of sandblasting. So if you make a new surface by steel grinding it, then perhaps you will have such an even surface that you will lose some possibility to receive a good bond. Now I'm coming to the end of my presentation. I will say some words about there is a European standard about repair of concrete structures, and it has a long heading: products and systems for the protection and repair of concrete structures, definitions, requirements, quality control, and evaluation of conformity. And this is a series of standards. And the number 10, the part 10, it is devoted to site application of products and systems and quality control of works. And we developed a new version of this standard some 5 years ago. And there we instead of we wanted the client to provide an alternative for the client to put requirements on surfaces to be repaired, or on substrates to be repaired. Instead of stating which method you should use, we wanted to use performance criteria, and we invented 3 of these, or not invented, we reused, I would say. So the first one is about cleanliness, and then it is a method that we have borrowed from other parts, that a clean white cloth of a specified material is moved in an S-shaped pattern on 3 surfaces. And so you should do all these 3 patterns on the very same surface. And then you check if the cloth is clean afterwards. And if it is, then you have you can be certain that the surface is clean. So this is the first method. The second one is to look at absence of microcracks, and then we have borrowed the method that was developed by Professor Luc Courard in Belgium by drilling cores, and then we are splitting the cores, and then we are investigating the top of the splitted core, and then we could measure the length of the microcrack on a certain area, and that will give us a measurement of the amount of microcracks. And finally, despite that roughness has a very minor importance, it is still easy to measure. So we could still measure the roughness, and that could indicate which type of method we have used. And then we could say that we should have a certain roughness in order to continue. That might be a little bit illogical, but on the other hand, it doesn't harm. So if you want to read more, there are a lot of literature, and there are 2 textbooks. One is Woodhead Publishing Limited in Oxford. There is a book called Failure, Distress and Repair of Concrete Structures. And I have written the chapter number 8 about bonded concrete overlays for repairing concrete structures. And you can read that. And then there is a RILEM. RILEM is the International Organization for Structural Laboratories. And they are making a lot of reports. And this is a state-of-the-art report. And the name here is Bonded Cement-Based Material Overlays for Repair the Lining or the Strengthening of Slabs or Pavements. And here there are, this is all, and the entire book is devoted to overlays. And here you can read about how to develop bond and how to compute the load carrying capacity, etc. And if you are Swedish speaking, you can buy this book from the Swedish Concrete Association, Svenska Betongföreningen, about industrial concrete floors. And there is 30 pages about overlays. And this will be my very last question. As a summary, I would like to answer the questions that I have received from the beginning. What is bonding? Bonding is the way of gluing two materials together in order to reach composite action. What is selectivity? That is the possibility to remove poor concrete while keeping the sound one. And why is it important to clean before recast? That is because dust may destroy the bond. And why jackhammers will damage the structure? That is because they are causing microcracks, and they apparently reduce the bond. So with this slide, I would like to thank you very much for your kind attention.